Assalamualaikum warahmatullahi wabarakatuh.
Welcome back to the deep dive. Today, we're getting our hands dirty, metaphorically speaking, with custom boat building.
Yes, specifically looking at building your own fishing boat.
Exactly. That dream of combining, traditional hands-on building with modern electric power, silent running, efficient.
It sounds ambitious, maybe, but it's definitely doable. You just need a solid plan.
And the sources we've got lay out that whole roadmap, right?
Pretty much, we can cover how to actually build a seaworthy boat using DIY techniques like stitch and glue.
Okay.
And then how to tackle the electric conversion part, sizing the motor, getting components lined up perfectly, even managing battery heat, which is critical.
Right. So our mission today is basically to give you the essential info you need to figure out that commitment. We want to cut through the noise and give you the details that matter.
From hull angles to battery chemistry.
Yeah, the nitty-gritty. Let's unpack this ultimate DIY challenge.
Sounds good. Because success here isn't really about luck. It's understanding the physics involved, both for the wood construction and the electrical side.
Okay, so let's dive into part one. Seaworthiness and whether electric is even feasible.
Safety first. If you want a boat that can handle more than just a pond, something for nearshore waters, maybe a bit choppy, what really makes a vessel seaworthy compared to just a simple little boat?
Well, it really boils down to the hull geometry, specifically something called dead rise.
Dead rise.
Okay, that's the V-shape angle at the transom in the back end. For going offshore, the sources are clear. Minimum 21 degrees.
21.
But if you want a hull that really slices through waves comfortably, that deep V shape, you're actually aiming for more like 24.5 degrees.
And I guess size matters too for stability.
Oh, absolutely. For operating safely outside really sheltered areas, you generally want a boat that's at least 16, maybe 18 feet long.
Right.
That length gives you the freeboard, the height above the water, and the stability needed for bigger waves.
Okay, whole basics covered. Let's switch to power. Electric's great, quiet, clean, less maintenance. But the big question is always range, isn't it? Always. And this is probably the most crucial thing to get your head around. Electric power really shines for low-speed, long-duration stuff.
Like trolling.
Exactly. Trolling or just fishing inshore. Maybe staying within 10 or 20 miles of the dock and then heading back to charge up overnight.
And the killer is that power curve everyone talks about. It's cubic.
That's the one. The power demand is cubic. So if you try to double your speed, let's say from 3 knots to 6 knots, you don't need double the power, you need 8 times the power.
Wow, 8 times.
Yeah. It means slowing down just a bit, say cruising at 3 or 4 knots, instead of pushing it at 6 or 7, can genuinely quadruple your range.
That has huge implications for design, especially with the weight of batteries.
It's a massive factor. Unlike diesel, where fuel burns off and the boat gets lighter, batteries are just dead weight, constant mass.
So how much heavier are we talking?
Well, get this. For the same range, an electric system, including the batteries, can weigh something like 9.5 times more than an equivalent diesel setup.
9.5 times. Okay, that's why you mentioned weight distribution is critical.
You got it. Structurally critical.
So if you're building a displacement hull, one that pushes through water, not planes on top, how do you size the electric motor? We have to think in kilowatts now, not horsepower.
Right. The general rule of thumb for displacement boats is about 2 kilowatts per ton of total weight.
2 kilowatts per ton.
But for folks used to gas or diesel numbers, there's a helpful conversion. Think of 1 kilowatt electric as being roughly equivalent to maybe 2 or 3 horsepower from a diesel engine.
Why is there such a difference? More bang for your kilowatt, basically?
Yeah. It's all about efficiency. Electric motors are incredibly efficient, like 85 to 95%, even when you're not running them full tilt.
Okay.
Combustion engines, though, they waste a ton of energy as heat and friction. So the electric motor delivers way more usable torque and thrust for its rated power. You can often get away with a smaller motor rating.
Gotcha. Okay, so we figured out the design, the power needs. How do you actually build the thing? Let's assume you're not buying a pre-made hull. What's the most accessible DIY method?
For most DIRs, we'd point towards the stitch and glue method.
Stitch and glue.
Yeah, it's great because you don't need a massive workshop full of specialized tools. You start with pre-cut marine plywood panels.
Okay.
You temporarily stitch them together along the edges using copper wire or even just plastic cable ties.
So like sewing a boat together?
Kind of. Then, once it has its shape, you make it permanent using thickened epoxy to create fillets, like structural glue joints, in the seams, and then you reinforce those seams with fiberglass cloth tape and more epoxy.
Sounds almost like boat origami with epoxy.
Yeah.
But if plywood is the core, the quality must be absolutely vital, right? You can't just grab any old sheet.
Oh, definitely not. This is
Oh.
non-negotiable. You must use proper marine-grade plywood. Look for standards like British Standard 1088 or the USPS 107.
What do those guarantee?
They guarantee waterproof glue WBP, water boil proof, very few internal voids or gaps, and no knot holes, using cheaper stuff like exterior grade ply. It's just asking for trouble down the line when moisture finds a way in. Structural failure waiting to happen.
Right. And that fiberglass cloth you mentioned, the e-glass, that makes the hard shell with the epoxy.
Exactly. Usually it's a 6 ounce per square yard woven e-glass cloth. It makes the surface incredibly tough. But, and this is a big, but epoxy itself hates UV light.
Sunlight degrades it.
Breaks it down fast. So that tough shell you build, it needs protection. You have to paint it or use a good marine varnish on every single exposed epoxy surface as soon as it's cured. No exceptions.
Okay, makes sense. Let's pivot to the motor itself. You mentioned converting a salvaged outboard is often the easiest DIY route. How does that work?
Yeah, it's often the most accessible path. You basically take an old gas outboard, strip off the power head with the engine part, but you keep the lower unit.
The bit with the propeller and the gearbox?
Correct. It already has your forward, neutral, reverse transmission and the prop shaft. Then you mount a new brushless DC motor, probably in the 2 to 3 kilowatt range where the old gas engine used to sit.
What's the trickiest part of making that connection work, getting the new electric motor hooked up to the old drive shaft?
The adapter plate and the coupling, that's the heart of the challenge. You need a custom machined piece, usually aluminum or steel, that precisely connects the motor shaft to the existing drive shaft in the lower unit.
And precision is key, I imagine.
Absolutely critical. The alignment has to be almost perfect. We're talking within 3 to 10 thousandths of an inch, 0.003 to 0.010 inches.
Wow, that's incredibly tight tolerance, tighter than engine building sometimes.
So stitching glue might be accessible, but this part sounds like it needs real precision engineering.
It really does. If you mess up that alignment, you'll get terrible vibration, heat buildup, and eventually the coupling will just tear itself apart. It's where meticulous attention to detail really pays off, or where things fail spectacularly. So if someone's budgeting for this, what's a rough ballpark for materials cost?
Okay, just for the home materials, plywood, epoxy, fiberglass, that sort of thing, for, say, a 16-foot boat, you're probably looking at somewhere between $2,100 and $3,900.
Materials only.
Right. Then the electric conversion parts, the motor, controller, batteries, wiring, all that could add another, let's estimate, $675 up to maybe $2,500, depending heavily on your battery choice and motor size.
Okay, let's zoom in on those batteries. They're the core of the electric system. If you're serious about this, building a safe, reliable boat, what battery chemistry should you be using?
The clear winner for marine use right now is LiFePO₄.
Lithium iron phosphate.
Exactly, LiFePO₄. It's got several big advantages. First, energy density. It packs about twice the power of old-school lead-acid batteries at roughly half the weight.
That helps with that weight penalty we talked about.
Significantly. Second, lifespan. You can expect 4,000 or more charge cycles, which is huge. And third, maybe most important, safety. The chemistry is much more stable thermally. It's far less prone to catching fire or thermal runaway compared to other lithium types.
Good to know. And voltage, we're not talking standard 12-volt car batteries here, are we? Why is 48 volts becoming the standard for serious electric boats?
It's physics, really. Ohm's law in action. For the same amount of power, a 48-volt system only draws 1/4 of the current compared to a 12-volt system.
Lower current means?
Means you can use much thinner, lighter, and cheaper wiring, like 10 or 12 gauge wire instead of thick, heavy cables. It simplifies installation, reduces heat loss in the wires, saves weight, saves money.
Makes sense. And it keeps you below that 60-volt threshold that's generally considered high voltage?
Precisely. Still needs respect, but it's generally manageable without extreme high-voltage precautions.
Okay, so you've got these LiFePO₄ batteries. They're heavy, potentially 400 to 800 pounds for a decent fishing setup. Where do they go, and how do you keep them safe?
Placement is critical. They have to go low down in the hull and centered, both fore and aft and side-to-side athwartships.
For stability and trim.
Exactly. And you absolutely need to reinforce the hull structure underneath them to support that concentrated load. As for safety, the enclosure they sit in must be waterproof. We're talking IP67 rated.
IP67 means submersible, right?
Yep, basically submersible for a short time, completely dust and waterproof,
Yeah.
and you absolutely need a BMS, a battery management system.
Why is that essential for LiFePO₄?
The BMS monitors every cell's voltage and temperature. It prevents overcharging, over-discharging, and balances the cells, which is crucial for both safety and getting that long lifespan out of them. You don't run LiFePO₄ without a good BMS.
Right. Now, the dream of solar power. Can you stick enough panels on a fishing boat roof to run it indefinitely? What's the reality check there?
The reality is generally no. Not for propulsion power on a typical fishing boat. There just isn't enough roof space, enough surface area to generate the kind of power needed to constantly offset the motor's draw.
So what are solar panels good for on a boat like this?
They're great for other things. They can definitely extend your range, maybe give you an extra 10 or 20%. They're fantastic for keeping the batteries topped up while the boat's docked or in storage. And they can run your lights, fish finder, radio, all the accessories.
Okay.
But for recharging the main propulsion bank after a day out, you'll almost certainly be plugging into AC shore power overnight. That's the practical reality.
Okay, makes sense. So fast forward, you've done it, you've built this amazing boat. How do you make sure it lasts and stays safe for years to come? Let's talk longevity and maintenance.
Yeah, you can't just build it and forget it. You need a regular maintenance schedule. The sources actually suggest budgeting about 10% of the boat's value each year, just for upkeep.
10%, wow.
It covers everything. Little things after each trip, like checking the bilge for water, monthly checks on fasteners and fittings, and then a thorough annual inspection and service.
What are some key maintenance points specifically for a wooden hull or deck? Anything surprising?
Well, for any wooden hull, moisture is the big enemy, always. After every single trip, you have to get any water out of the bilge and make sure it dries completely to prevent rot.
Okay.
And here's a specific one for teak decks, if you have them. Never, ever scrub teak with the grain,
Why not?
because it digs out the softer wood between the hard grain lines, and you end up creating ridges. It ruins the deck over time. Always clean gently across the grain with a soft brush or pad. And maybe controversially, skip the teak oil. It just attracts dirt and means constant reapplication. A clean, natural gray is often better.
Huh. Interesting. And performance-wise, neglect can really cost you, can't it?
Yeah, take hull fouling barnacles and slime. Just having 10% of your hull covered in growth can force your engine to work 36% harder to maintain the same speed.
36%. That would kill your range on an electric boat.
Absolutely hammers it. And for the motor, if it's an outboard conversion, you need to change that lower unit gear oil annually. Check the old oil if it looks milky or coffee colored.
Water got in.
Yep, means the seal has failed and water's mixing with the oil. Needs immediate attention. Also check the propeller regularly for dings or damage. Even small nicks can cause vibration. File them smooth. And replace the sacrificial anodes. Often they protect the metal parts from corrosion. Okay, last checks. Before you even put the boat in the water each time, what are the absolute must-do safety checks? Especially the ones people forget. Number 1, hands down, the thing that sinks more boats than almost anything else, stupidly simple, put the drain plug in.
Don't forget the plug.
Seriously, it happens all the time.
Yeah.
Number 2, and this is more structural, check your through-hull fittings and their valves, the seacocks.
Yeah.
These are holes below the waterline for things like engine cooling water or drains.
Right.
They must be made of proper marine bronze or an ABYC-approved engineered polymer. Never use cheap brass or plastic fittings below the waterline. And make sure the seacock valves open and close smoothly. Keep them lubricated. If one fails stuck open or the fitting breaks, well, the boat can flood very quickly.
Okay, good advice. Also, what about registration? You built this thing in your garage. Do you need paperwork?
Oh, absolutely. Home-built boats still need to be registered with your state or territory, just like any other vessel. You'll likely need to apply for a hull identification number, HIN. And of course, you need all the required safety gear for its size PFDs for everyone. Fire extinguisher, nav lights, sound signals, etc.
Right. Okay, so we've taken this dream project, the custom electric fishing boat, and really put it through a reality check. What's the main takeaway for someone listening who's thinking, yeah, I want to do this?
I'd say the biggest takeaway is that, yes, it's achievable. You could use accessible methods like stitch and glue. But success really hinges on meticulous planning up front.
Plan everything.
Everything. Using only high-quality marine-grade materials. And setting truly realistic expectations, especially about range with electric power and patience. A medium build might take you 5 to 8 months of pretty consistent work.
And for the electric side specifically?
Careful battery management, the BMS, is key, and getting that weight placement right. That's often the make-or-break factor for electric builds.
It sounds like an incredible journey, though, blending that old-world craftsmanship with cutting-edge tech. Okay, here's a final thought to leave everyone with. We talked about the huge weight of these battery banks, maybe 400, 800 pounds, all concentrated. How might boat designers in the future start thinking about actually using that battery mass as part of the boat's structure itself, turning that weight, currently a disadvantage, into maybe a structural keel or integrated reinforcement?
That's a fascinating question. Using the battery mass itself as integral structure. Something to think about.